So hello everyone, welcome to this class. So today we'll continue, let me just share my screen. Okay, so we'll continue from where we left last time. Okay, so last time we were looking at understanding how MIMO and OFDM fits in. Okay, so I want to start with if you have any questions or concerns here, I can repeat some of the stuff and then we can move forward. Hello, am I audible?
Yes, sir, you are audible.
Okay. So any questions or we can proceed further? Did you understand this part? Okay, so the main crux is that every resource element acts like a one MIMO channel. That's what you should remember. Every resource element acts like a one MIMO channel. Okay, that's what we saw. Na? Each resource element. So if we have an effective channel, so we have an effective channel. Okay, that maps multiple. One resource element to which acts like a MIMO to each resource element. Okay, so in each time frequency point, you get a MIMO channel. Okay, so if there you have X number of resource elements, you have X number of MIMO channels. Yes. Is this clear?
Sir, what is the significance of pre-coder? Because it is simply multiplication factor, na? Then what is exactly the pre-coder?
Yes, sir. Okay. See, I mean, till now you are taking simple examples where there are 2 antennas, 3 antennas. So let's just do this again. So now I look at the case. So now that we know that how OFDM and MIMO integrates, essentially it's MIMO for each resource element. Okay, and there's a channel for that independent channel. I mean, there's a single tap channel, MIMO channel for each resource element. Okay. So now let us talk about the precoder. So what did we say? So we have bits which are mapped to the constellations, and then we have something called the layer mapper, okay, which gives number of layers, and there is multiple number of antennas. Yeah, I'm talking about single resource element. Okay. So if this is number of layers is NL and this is number of layer antennas is NT, you multiply with a matrix called NL cross NT. This is called the precoder. Okay. Okay. So you might have one layer, you might have 64 antennas. What will the precoder do? One simple precoder is that you send the same data through all the antennas. Okay. In that case, how will your your precoder will be 1 cross 64, essentially be 1 1 1 1 1. Okay. So you multiply with the same data x. Okay. This will be the output. Output will be x x x x x. Everywhere in the same data goes to that. You might have more complicated precoders, but precoders are always matrices. Matrices means the linear operations. Okay. Chitranjan, does this answer your question?
Sir, that means if pre-coder all the values are 1, then also that will do, na?
Anything you can. A precoder is up to you to decide. How you choose your precoder is up to you.
Okay. It is just used to map from NL to NT.
That is one of the use. I'll tell you one more use today. Okay, I'll tell you one more use today. Fine. Okay. This is one thing. So, I mean, one more thing that day we saw in the class was that effectively the channel will be equal to. Okay. Let's not do this right now. Okay, let's understand this precoder business a little bit more carefully today. Nice. Okay. So this is how the equation was. No, that's what we saw. I mean, sometime back, HPX plus precoder, X multiplies precoder, and precoder goes into the channel, and that's what you get. Okay. So there are two cases. One is called CSIR, channel state information receiver. We saw that for CISO also. Okay, but the same thing holds for MIMO also. CSIR means channel state information at RX. And the second case called CSIT, channel state information at TX. Okay. So CSIR is the most common. You require channel state information at the receiver. What do you mean by channel state information? Channel state information means you estimate the channel at the receiver. Okay, you know the channel at the receiver. Okay. So we also saw how if you know the channel at the receiver, then how do? You do pseudo inverse or you do simple 046 to recover your data. Okay. Okay. So now let's discuss this a little bit. So first let's start with the case of CSIR. Y is equal to H times Px plus N. Okay. Let's only consider the case of CSIR, channel state information at the receiver. Okay. The first thing is, so now from a receiver perspective, X is the data, Y is the received signal. There are two options. One. Okay. P is base station informs UE. I mean, the same thing holds in the uplink also. I'm just doing the downlink about P. Because somehow, let's not worry about that right now. We'll discuss that later. Somehow, base station tells the UE, hey, that I'm using this particular matrix P. Okay. The second thing is base station does not inform UE about P. Okay. So the first question I want to ask you is, I want you to think about this a bit. Does it really does the base station really require to inform the UE about P? Is it necessary?
If it informs that UE, then it will be better for the UE to get that channel response.
Yeah. So, but if you think about this, UE is interested only in X. UE is interested only in X. So, according to the UE, the effective channel is H tilde. Okay, where H tilde is nothing but precoder. It is not worried about what is H, what is P. Okay. But nevertheless, what you say is true. Okay, I'll come to that point later. So one thing what we can do, what generally happens is, based on the pilots, UE can estimate H tilde. I will come to that, how it estimates H tilde. Okay, but let's now assume that it can be done. Okay, so effectively the UE will estimate the effective channel H tilde. And then what does it do? It can do H tilde pseudo inverse. Pseudo inverse is represented like this to get back X plus, okay, to get X hat estimate as pseudo inverse time Y. We saw pseudo inverse last class. Okay. So these two cases happen in the standard. Okay. There are some reasons why this will happen. I will just wait for a few more minutes. I will tell you. I'll tell you a little bit about this. Okay, this has to do with analog beamforming. So for now, with CSIR, so essentially when I say CSIR, effective the UV will know the effective channel, which is H tilde from the pilots, and it inverts. Fine. Okay. So now let's look at CSIT. Okay. So the assumption is UV estimated channel, just the plain channel, and thread it back to base station. Okay, so effectively the base station. So the base station knows.
Sir, in that UE estimate the H tilde, na? H hat.
No. So not H tilde. I'm assuming that somehow the UE is able to estimate H, just plain H without precoder. There's no precoder. Okay, this is the first step. Suppose the UE is able to do, and it transmits this H. Maybe I'll just put as H hat because it's an estimate, but maybe I'll just write it as H. Okay, so the base station knows H. Suppose the base station knows H. What can you do? How do you choose? So let's for simplicity also assume that H is 2 cross 2 matrix as a square matrix. Okay, and the UV also wants to transmit. The base station also wants to transmit 2 layers. For example, let's take the example of 2 cross 2. Everything is 2 cross 2. How will you choose your precoder? What is a smart way of choosing your precoder? You know H at the transmitter.
H inverse.
Fantastic. Okay, so what will the base station do? The base station will choose P is equal to H inverse. Okay, then what will the UE receive? You will receive H inverse X plus noise. This is what the base station is transmitting and the channel. So this is equal to X plus noise. Okay. So what I want to tell you is the precoder can be equal to channel inverse. Okay, I mean there are some constraints on this, but in a general sense, this can be done. So what is the difference between this? Why is this a more advantageous than this equation? Okay, so let me just write up this equation again here. I have my y effective y tilde is equal to X plus pseudo inverse noise. Look at this equation 1 and look at this equation 2. Okay, what is the difference between these two? Okay, let's do a simpler thing. Okay, suppose my channel is let's get back to CISO case. Okay, let's get back to CISO case, and let me say my channel is 0.2. Okay, first case is CSIR. Y is equal to, this is what you receive, 0.2x plus noise. Okay, what do you do with the receiver? You divide by 0.2. Okay, so you say y hat is equal to y divided by 0.2. Is equal to x plus n by 0.2. Okay, this is your equation. Okay, this is your first equation. Okay, CSIT, same h is equal to 0.2, but what you transmit is you transmit x by 0.2, so you get this. There is some cheating I am doing, but I'll tell you that later. Okay, so here my y hat is equal to x plus n by 0.2. Here my y is equal to x plus n. Which of them will give you better performance? This one or this one?
First one.
First one. Why?
Because noise has been reduced by by H.
It's by divide by 0.2. 0.2 is smaller than 1.
Sorry. So two is there. Two
Yeah,
is
2 will
very
give.
big.
Okay. So what might happen in this particular case is if the channel is bad, your noise will get boosted. Okay, your channel is bad, When you have CSIR, when you invert the channel, the receiver, your noise boosting happens. Here you don't see noise boosting. There's no noise boosting. Of course, this is a very, very well-crafted example. Okay. So in general, what happens is, I mean, I'm not telling you the exact technical things in this. I'm putting a lot of things under the carpet. CSIT gives you a better channel capacity. Effectively, the channel capacity of CSIT, when you use your precoder to cancel your, what do you say, channel, will be much better than just plain old CSIR. CSIR is anyway must. CSIR is always there. CSIR is the base case. Okay. I mean, you can show this in a more rigorous manner. Okay. The CSIT will always be better than CSIR.
Sir, but in CSIT, estimating the exact channel is very difficult.
Yeah, I mean, given all that, okay, given all that, okay. So I'm just telling you the vanilla case. There's lots of issues in the CSIT. Okay, I have not told you that. Okay, generally there's also something called a power constraint at the transmitter. When you divide by this thing, you may violate the power constraint at the transmitter. Okay, but forget about all that. Okay, those are all next level of issues. From a high level issue, if you know the channel exactly, it's better to invert the channel at the transmitter. Okay, is this clear? Okay.
Yes,
I'll tell you a better CSIT example. I mean, I'll tell you how they do it actually in practice. I will tell you that one minute. Okay. So did you understand the difference between CSIT and CSIR? So precoder can also precoder essentially effectively what it does is it tries to invert your. I mean, one of the ways of using the precoder is to invert your channel. I mean, effectively cancel your channel. Yes. So the next question is what happens if H inverse doesn't exist? If H is not a square matrix, what happens? What happens if it's not invertible? All those issues are there. Of course, there are solutions to all of them too. I'm going to tell you the most common way of doing this. Okay, so this is your channel. So I'm going to take this specific case of that H is NR cross NT channel. Okay. The first step is you don't use any precoder. Okay. Don't use precoder. I'm just talking about CSIT case. Let UV estimate H and feed it back to the base station. Okay, so now the base station will get an estimate of H. Okay, that is what is called H hat. H hat is the estimate of H. So if your SNR is good and other things, your H hat will be closely equal to H. Okay. Then what generally is done? Okay, I mean, I'm just telling you this as a fact. What is done is H is decomposed using something called SVD decomposition. Singular value decomposition, SVD. Okay. So what will be the size of U is, U will be an NR cross NR. This will be an NR cross NT. V will be an NT cross NT matrix. Okay. And there's some speciality of U and V. U is a orthonormal matrix. What that means is U Hermitian is the inverse of U. U Hermitian U is equal to I, and similarly V Hermitian V is equal to I. Okay. So if you want to find the inverse of U, all you have to do is you have to take the Hermitian of that. Okay, that will automatically become the inverse. Fine. I mean, just know this. I mean, the details of this you can study, or if you are any of you interested, you can make. I mean, I can give you more material on this. Okay, this is called the singular value decomposition. Then what the base station does is, okay, so
sir,
now
can you explain it again, sir? Sir, can you explain it again, sir?
Okay, fine. So H is somehow known as the transmitter, the base station. Okay. So there is something called singular value decomposition. Singular value decomposition means you write H of a product of three matrices. Okay. U, V are U, V, U, sigma and V. Okay. Sigma is a diagonal matrix. Diagonal matrix with singular values. I'll tell you what this means. Okay. The diagonal. Okay. U is an orthonormal matrix. V is an orthonormal matrix. Okay. So you will be able to decompose any matrix like this. Any matrix can be decomposed as U sigma V. I mean, generally they put U sigma V transpose, but I'm just to avoid confusion, I'm just dropping off the transpose here. It doesn't matter. Okay. So you can decompose as U sigma V. Okay. So there are three matrices. The beauty of these matrices is U is an orthonormal matrix. Okay. What does it mean? Means, so if you take any matrix, okay, for example, you take A is equal to 0.3, 0.3, 0.5, 0.7. Okay. What is the inverse of the matrix? You can compute the inverse of the matrix. There's a procedure to compute the inverse of the matrix. And what is the property of inverse? A inverse into A will be equal to identity. What is A transpose or A Hermitian is not complex, so you can take A Hermitian or A transpose will be the same. 0.2, 0.5, 0.3, 0.7. Essentially, you invert the rows and the columns. Okay, the columns become the rows and the rows become the column. Okay, it is all. You can try this out. A Hermitian into A will not be equal to identity in this particular case. Okay, but for example, you take A is equal to 1 by square root 2 minus 1 by square root 2, 1 by square root 2 and 1 by square root 2. For example, A. Okay. Then A transpose A will be equal to identity. What does this mean? If some matrix into A is equal to identity, that some matrix is nothing but the inverse of A. So then A inverse will be equal to A transpose. Okay, you can check this. You do the A transpose and A transpose into A will be equal to identity. Okay. So this is an orthonormal matrix. Okay. So for an orthonormal matrix, I'm just giving you the example of a real case, but in the complex case, instead of transpose, it will be Hermitian. When you do the transpose, you also do the conjugate. Okay. The property of U is U Hermitian into U will be identity. So essentially, U Hermitian is the inverse of U. Similarly, V Hermitian is the inverse of V. Okay. So these are called orthonormal matrices. Fine. So any matrix can be decomposed as H U sigma V. Okay. And what does the sigma contain? That's more important. H is equal to U sigma V. There's a transpose. Generally, they put a transpose here, but it's okay if you don't put that one also. You can do all the math without the transpose. It just confused for the first time. It will be confusing. So I'll just put U sigma V. Okay. So the V is automatically transposed. It's okay. So we saw one thing that we saw in the earlier class was the rank of the matrix plays a critical role. You cannot transmit more than the rank of the matrix, the number of independent columns or rows in the matrix. Okay, and we also saw that rank of H will be always less than or equal to minimum of NT comma NR. Okay, so what does sigma contain is, sigma contains something called the singular values. And how many singular values will be there? The number of singular values will be equal to the rank of the matrix. Okay. So remember, U is an NR cross NR, V is an NT cross NT. So sigma will be an NR cross NT matrix. If you look at the diagonal of this matrix, everything else will be zeros except the diagonal. Okay. So in the diagonal, the number of non-zero terms equal to the rank of H. Okay. So effectively, if the rank of H is 2, then you'll have only two diagonal terms. All other things will be 0. Okay. So the maximum number of elements in this will be minimum of NR comma NT. If it's a square matrix, for example, NR is equal to NT, the entire diagonal will be maybe non-zero. If the rank is full, it's a full rank matrix. It's invertible. So I'm going to put some properties to a square matrix is invertible if and only if it is full rank. Okay. So one of the thing properties is full rank also implies determinant is non-zero. Fine. So did you understand about the singular value decomposition?
Sir, here the matrix is not square, then diagonal will be upper diagonal or lower diagonal.
Yeah, that's right. Only minimum. So the maximum number of non-zeros rank is anyway bounded by this. Minimum of nr comma nt. So maximum number of, for example, if you have a 2 cross 4, okay, it will be like this. Only maximum 2 will be there, no? Non-zero elements. Chitranja, is this fine? What you say is absolutely true. Okay? But you see that the rank is always less than minimum of nt comma nr, and the number of non-zero elements is equal to rank of it. So it will fit in properly. Okay. So what is the use of this whole thing? Okay. So now you have h is equal to u sigma b. So I have y is equal to h times pre-coder times x plus n. This is what I want to transmit now that I have estimated my channel. So what will I choose my pre-coder as? I will choose my pre-coder as V transpose. Okay. So V transpose V is equal to I. So V into V transpose is also equal to I. So what will happen is I'll put my pre-coder as V transpose. V transpose x plus noise. Okay. So what will be my y? So now if you think about the decomposition, it will U sigma V transpose x plus noise. Okay. What is V transpose INT? Okay. So this will be U sigma x plus noise. This is what the receiver will receive. Okay. Still the matrix is mixed. So now what will the receiver do? What will receiver do? Receiver will multiply by, so this should be U Hermitian, okay, by U Hermitian. So U Hermitian y will be equal to U Hermitian sigma x plus U Hermitian noise. This is equal to U Hermitian, U Hermitian U, okay, there's a U also, no? So U Hermitian U will be INT. So this will be sigma x plus U Hermitian noise. Okay, I'm just going to write this as y tilde. Okay, I'm going to write it here. So I have y tilde is equal to sigma x plus n tilde. N tilde is U Hermitian. Okay, it turns out when you multiply noise by a orthonormal matrix, noise boosting will not occur. Okay, you can show that the variance of this n tilde is equal to the variance of n. So the noise boosting will not occur if it's a Hermitian matrix. You multiply with a Hermitian with a orthonormal matrix. Okay, so this noise n tilde is in the same as in same rough. The statistical properties of n tilde are the same as n. Okay, but the beautiful thing that happened is you got sigma into x. Okay, remember sigma is a diagonal matrix. For example, if it was a 2 cross 2 matrix, if everything channel was a 2 cross 2, what will sigma be? Sigma will be 0, A, B, 0. Or maybe, no, I'll not put A, B, I'll put it as something else. I'll put it as lambda 1, lambda 2, both the singular values of h, 0, 0, x1, x2 plus noise. Okay. So if I rewrite this properly, so if you take this diagonal matrix and multiply this, what do you get? Let's write it in the next page. Y tilde is equal to lambda 1, lambda 2, 0, 0, x1, x2 plus whatever n1 tilde into tilde. Okay. So if you think about this, this is nothing but you will get two equations. Y1 tilde is equal to lambda 1 x1 plus n1 tilde. Y2 tilde is equal to lambda 2 x2 plus n2 tilde. Okay. So effectively you got two parallel channels. Okay, there's no interference of x1 to the other channel. There's no interference of x2 to the other channel. Okay, remember our original micro channel. If you transmit x1, x2, get some linear combination of x1 and x2. And similarly, you will also get a linear combination of x1. Okay, but now the interference is gone completely. So effectively, what you got are two parallel channels. Sorry, 1 minute. Just just 1 minute. Sorry, my screen. Then suddenly something happened. And, yeah. Okay. Is this clear? So this is the most optimal way of choosing your precoder in some sense. Okay. So what you do is at the transmitter, you find a singular value or decomposition of the channel, and whatever is on the right side, the orthogonal matrix V, you choose the Hermitian of that matrix as your precoder. And by that, what you can do is you can remove the interference, the interstream interference between all these things at the receiver by simple processing at the receiver. Okay. So one thing that you observe is you finally get multiplied by lambda1 and lambda2. Okay. So the effective data rate that you can support in each of this channel depends on lambda1 and lambda2. Okay. Okay. So one more trivia point is determinant of the matrix H is nothing but product of all the lambda is. Okay. So lambda1 into lambda2 and other things. Is this clear, everyone? Did you understand what I have done?
Sir, here we are assuming both CSIT and CSIR, right?
Yeah, CSIR is, I mean, if you have CSIT, you'll obviously have CSIR.
Okay, yes, sir.
So without CSIR, you cannot do anything.
Yeah.
So you understood how we decompose the channel, and we can use the channel right, whatever the right, the V channel as your precoder, and the U channel will be, U channel will be inverted by the receiver. The inversion is also very easy, straightforward, because you have to just multiply by U Hermitian. You don't even have to invert anything. Okay. It turns out that this is the way you achieve the capacity in MIMO channels. You can immediately see one important property that you can see is effective channel. Effectively the whole thing looks like, after you do all the operations, it will be looking like Y is equal to sigma X plus noise. Okay. Remember, the number of non-diagonal, see, essentially sigma is a diagonal matrix. X is what you are transmitting, X1, X2, some number of streams you are transmitting. Okay, whatever NT you are transmitting. Okay, but if your sigma, if the rank of your matrix is only 3, for example, then you'll have lambda1, lambda2, lambda3, everything else will be 0, even diagonals also. Okay, so effectively you'll have only 3 parallel channels. All other data will not go through. Okay, you can immediately see the effect of rank through this lambda1, lambda2, and lambda3. Agreed? There's one more thing generally people do. They also invert for lambda1, lambda2, 3 here by multiplying with lambda1 inverse, lambda2 inverse, and lambda3 inverse. Okay, again, I'm not telling all that, but but you just know that can happen. Okay, is this clear? Any questions before we proceed?
Sir, in CSIR, the UE will estimate the H hat and it will feed back to the base station.
Yes.
But that feedback will also happen in the same wireless medium. So then that channel effect is also will be there in the feedback.
Very awesome question. Actually, very awesome question that is. Okay, so let's talk about that question. So this is where, okay, so you're talking about channel estimation and feedback. Let's discuss these things now. Okay, let's start from a very high level. Let's answer Chitranjan's questions. So what is Chitranjan saying is, this is a base station. Okay, the base station somehow, let's not even worry how it sends pilots, some pilots, and the UV estimated the channel pitch. Okay, somehow it did a very careful, very great algorithm and estimated H hat. Okay, the UV has to feed this back to the base station. Okay, so let's assume for simplicity that it's NT cross NR and let's assume a 3 cross 2 cross 2. I mean, okay, it's an NT cross NR matrix. Now the UV has to feed this back to the base station. Okay, for the base station to know it, UV has to feed it back. How will the UV feed it back? UV has to still feed it back using the wireless media. Yes. So, first of all, how many elements are there in this? There are NT, NR elements. Elements means complex numbers. Okay. So if there are NT and R complex numbers, I mean, depending upon your size, the number of antennas in your base station and the number of antennas you this may blow up very quickly. For example, if the base station has 64 antennas, for example, I'm just giving an example, 64 and I mean not 64 antennas, 32 antennas, 32 ports, and the UV has 4 antennas. You are talking about 32 cross 4 channel estimation feeding back. 32 cross 4 is about 128 complex values you have to feed back. Each complex value, if you assume that at least you are giving it 32 bits, you're talking about a large amount of data that has to be fed back. Okay, the issue is, one issue is large amount of feedback, and the second thing is this feedback is also not reliable. Okay, because you are using the same wireless media to feed it back. Okay, it's not reliable. Okay, so what is a good way of solving this problem? Okay.
So can UV also transmit some pilots to base station and then
it will do all that. It will do all that. Dipanshu, it will do all that. Still, it's a large amount of data. The feedback is not reliable. Okay. So, but let us look at this problem a little bit carefully. So, we saw H is equal to U sigma V. Okay. What does the base station require to know? Does it require to know U and sigma? It requires to know only V, or at most sigma and V. Yes. It does not require to know U. Yes, because what is the base station doing? The base station's precoder is just V transpose. And now, if you want, you can invert sigma also. Sigma inverse if you want to. Okay. Sigma has only few values, so let's forget about sigma for now. Base station has to know only V transpose. Yes, base station did not know the entire H.
V Hermitian.
V Hermitian, sorry. V Hermitian it should know. Yes. So what they do is, generally, this is not always universal. Generally, they feed back V Hermitian. Okay. But again, the same problem is still there. The V Hermitian also has a large number of entries. How do they feed back V Hermitian? Okay. Here is where they use something called code books. Okay. So what is a code book? So let us understand this. Okay. So let us understand this with a simpler example. Suppose, let's take this case of CISO channel. Y is equal to 0.2567x plus noise. Okay, suppose this is the channel that you have. Okay. I'm just giving a hypothetical example. So the UV somehow estimated that my channel is equal to 0.2567. Exactly, it estimated somehow. Let's not worry about that. Okay. Now you have to feed this back. You have to feed back 4 decimal places. Okay, this is a painful thing. So one thing you can do is you can feed back this entire thing as it is, which may take a large amount of data. Or what you can do is assume that the channel lies between 0 and 1. You break it into 4 parts. 1, 2, 3, 4 parts. Okay, 0.25, 0.5, 0.75. You quantize it to the nearest value. So this is your code book. Code book means whatever value you get, you quantize it, you map it to the closest value. Okay, so in this case, you will map this 0.2567 to what? You will map it to 0.25. Okay. Okay, you map the channel estimate to the closest value in the code book. Okay, so in this particular case, what do you transmit? So essentially, the UV will transmit 0.25. Okay, it will not transmit 0.25. It will transmit the index. So they will call this as 0, 1, 2, 3, 4. Okay, so how many bits are required? 0, 1, 2, 3, 4 means extension 3 bits are required. So it will send 1. It will the what UV transmits to the base station is number 1. So when the base station sees number 1, it will map 1 to 0.25 and say, okay, whatever the UE has seen must be very close to 0.25. So I'll use 0.25 as my channel. Is this concept clear?
Yes.
Yes. So one thing you can see, if you want more and more accuracy, you have to increase the more and more number of points here. Okay, your code book size increases. So number of bits you have to feed back, number of bits to be sent to the base station is equal to logarithm 2 of number of entries in the code book. Entries in code book. Okay, at least the ceiling of this. Okay, so if you have 8 entries, then you have to send 3 bits. If you have 16 entries, you have to send 4 bits. If you have a larger number of entries, you have to send larger number of bits. But one thing is sure, that as the number of bits are increasing, your accuracy of your channel estimate becomes better at the base station. Okay, but just feeding more number of bits. Okay, so this is called as code book quantization. Okay, I mean, this is in one dimension it's called quantization, in a higher dimension it's called code book. I mean, vector quantization or code book based quantization. Okay, is this clear? So now let us understand. So now the question is, now you have to transmit V. Okay, so what they do is, I will not go into the technical parts of this. See, one dimension we are really able to understand how to do the quantization. I mean, it's a straight line, you break it into small parts and you see where the value falls and you send it back. Okay, but for now, V is a channel of size NT cross NT. Okay, it turns out there is some concept called as Grassmannian manifold quantization. Okay, those of you interested can look at this technical term. Okay, so what they do is, effectively what they do is, they also have code words, a large number of code words. Okay, some NQ code words. What they do is, they map the matrix to the closest code word. Map the matrix to the closest code word and send the index of the code word to the base station. Okay, so from that, the base station also will have the same code word. So from the index, it will also know, okay, this is the closest, what do you say? What is the closest matrix to the actual channel matrix? Okay, so the notion of closest is very important. Okay, there's a lot of research on what do you mean by closest in terms of matrices and other things. Okay, so I mean, there's a lot of work on that, on how do you find the closest matrix in this Grassmannian manifold. Okay, so but let's not get into all those things for now. Let us what happens is, the specification decides a particular code book. The specification gives you a code book. You pick out one of the matrices from the code book which is close to your matrix that you want to transmit, and send the index of the code book. Index of the code word. Okay, is this clear? Chitranjan, does this answer your question at least partially? Okay.
Yes. Yes.
So I'm going to go into a little bit deeper on this. Let's discuss this. Okay. Base station is there. First, let's take the case of FDD. Okay. FDD means the downlink happens in one frequency, the uplink happens in the different frequency. Okay. So in this case, what is going to happen is the base station is going to transmit in this frequency. Okay, maybe first let's do the TED part, and then this will become clear. Okay, let's do the TED part. So in TED part, so let's just so TED part, how does the base station? So for example, this has 64 antennas, this has 2 antennas. Okay, what happens is the UBF transmits the pilots in the uplink. We call the SRS pilots, sounding reference signals. The base station estimates the uplink channel. Base station estimates uplink channel. Okay. So when the base station is transmitting, you will transmit in the same frequency. This is a TED case. The base station will transmit in the same frequency, but in the downlink. So by channel reciprocity, so it will estimate, so the uplink channel will be equal to NT cross NR. Okay. By channel reciprocity, the downlink channel is equal to uplink channel. Okay. So what will the base station do? The base station will actually use the uplink channel for the downlink also. I mean, you just of course transpose it. Just do a transpose because it's NT across NR, it will become NR cross NT. Okay. So that is the reason why massive MIMO is very, very popular in TED bands and not in FDD bands. The main reason is that the uplink pilots can be used to estimate the downlink channel, where the downlink is where you push in a lot of data, na? But you can use the uplink pilots to estimate the channel. There's no specific channel feedback that is required. No specific channel feedback is required. Is it clear? Okay. On the other hand, if it's an FDD system, you can't use a reciprocity. So first, what the base station does is the base station transmits something, pilots. UV estimates the channel H hat, goes to code book, finds the index, and transmits the index back. Okay. So in general, in FDD systems, the code book based precoder is used. Whereas in the TED systems, the channel reciprocity is used to use the uplink channel estimate for the downlink channel also. Is this clear? Okay. That is why massive MIMO is generally done in TED bands. Whereas in FDD bands, you don't use so many antennas because the code book sizes become larger and other things. So as the code books have to be fed back. Code book indices have to be fed back. Is this clear? Any questions?
In that y equal to sigma x plus n, the rank of sigma should be less than or equal to number of layers as well, right?
See, it's a diagonal matrix. Okay, so I mean the rank of it is of course less than NR and T, but the number of non-zero elements in the non-zero elements in the diagonal will be equal to the rank of H.
No, NR and T, and also it should be less than or equal to number of layers as well.
Yeah, it will be. I mean, number of layers should be less than or equal to NR and T. Okay. So you understood the difference between FDD and TED. Why TED is used in why TED is used for massive MIMO 5G. That is why the reason why 5G generally talks about TED spectrum and not an FDD spectrum. Okay, because if you want to use massive MIMO. Okay. So at this point, I'm going to stop. Still, we have. I thought I'll finish the channel estimation part today. Tomorrow, I'll do that next class. let's go and look at the questions. Let's take at least 10 minutes and look at few questions, and then we can do the next set of questions in the next class. Okay, let's begin with the questions. So I just copied the questions into a Word document and started writing the answers. So the first question is, I mean, I will just leave it for you to read. So essentially, what yeah. So this is the, I mean, let me just talk about this channel raster and synchronization raster, right? And I'll provide more details in the coming classes. I'll also, I mean, send you a different note. I'll send you the note also. So one thing that is different between LTE and 5G NR is this whole notion of synchronization raster. Okay, channel raster was there also in LTE also, but synchronization raster is something that has been introduced in 5G NR. Okay, so these two rasters are different, and the synchronization raster generally, what do you say, has a different, what is it called as, not resolution, the delta, that whatever how much you search every time, that's different compared to the channel raster. Okay, and the other thing is the location of this synchronization block, SS block in LTE was fixed. It was fixed to the channel raster. Whereas in NR, the SS block is related to the synchronization raster, and the location of the 0th subcarrier depends on the channel raster. Okay, that's one major difference between NR and LTE. Okay, so where are these details provided? These details are provided in, I'll open up the document. Maybe not this, but you know. The channel raster and these things are providing 38101, 38104. Okay, where they talk about the channel raster first, and then they talk about the synchronization raster. Okay, not only they talk about the channel raster and synchronization raster, they tell you how the channel raster is mapped onto the resource block. Which resource block is it mapped to? Okay, so that part is also specified here. Okay, so similarly, how the synchronization raster is mapped to, which resource index is it mapped to in the SS block, is also provided by the specification. So what I'm going to do is, I'm going to scan one doc. I have a document. I have it from a book. I will scan that part and put it online. Okay, you first have a reading of that, and then we can have a offline discussion. Whoever has a question we can have an offline discussion on that particular part on how channel raster and synchronization raster are mapped onto specific frequencies. Okay, if you read that, it will become much more clear, and then we can have the discussion. Okay, so other question that is there is, cells using larger channel bandwidth can transmit multiple SS blocks distributed across the channel bandwidth. The specification does not prevent it. The specification does not, does allow you to do that you can, in the same slot, you can transmit multiple SS blocks across the frequency. Okay, this is certainly allowed. So, but the only thing is that MIB that is encoded in this has to change because the offset to point A and other parameters inside the SS block has to change. Okay, that's the only thing. But the question is, the more important question is, why do you want to do this? What is the, I don't know who asked this question, but why do you want to put multiple SS blocks across different frequencies? What is the point of doing that? Okay, why do you want to do that? I don't know who asked this question though. Okay, so these you don't have to do this because The SS block is of very small bandwidth. Okay, it's just 240 RS. Okay, every UE will be able to decode that 240 RS anyway. Okay, I mean they may be spread across different I mean it will be spread. It will be there in any of the 100 megahertz bandwidth, but nevertheless a UE has to decode them. Having a larger number of SSBs in the frequency domain parallelly will not. I mean I don't think will help us out in any in any manner. Okay, the spec does not prevent it. You can do that, certainly do that. Except that the only concern is the index of all this should be the same, because the index only changes on a slot by slot basis. Okay, so what I'm going to do from my side is I am going to put some documentation on the channel raster and mapping to the RET. Channels as sync raster. Okay, specifically on the mapping to the DC subcarrier. Okay, and other things. I'll put a detailed note on this. Okay, once I put the note, we'll have a discussion on this again. Okay. So this next question on how multiple subcarrier spacing with respect to LTE and 5G NR can happen. I'm not very sure of this. I have to read this. So what I'm going to do is I'm going to take some time, read this, and come back and answer this. I mean, I'm not very sure on how LTE and 5G NR coexist when they do the this thing NSA mode. I'll get more details. I mean, in a few more, give me a little bit time. I'll find about this. Okay. The third question is ZC sequence is generated by the UE, but not by G node B, and G node B sends the base station sequence number, and then how does G node B correlate the ZC sequence received from the UE? What you say is absolutely true. The base station is the master, and the base station transmits what is the base sequence number that has to be used in the patch. It transmits this in the SIB1, in the SIB message called patch root sequence index. Okay, so both the UE and the base station know what is the base sequence. Because of this, the same base sequence can be generated in the base station, the UE, and this can be used for correlation. Okay, does this make sense?
But where does this ZC sequence will be generated in the BTS?
Sorry, Vijay, can you repeat it, please?
Which element will generate this ZC sequencer in the base station?
The patch receiver. Hello, Vijay. The patch receiver does this.
Okay.
The patch receiver, whatever module does the patch receiver has to generate this.
Okay, sir. Yes, I'll check once.
Okay, so Pranit, it says that is a DC subcarrier located at the midpoint of the total PRBs. No, I mean DC subcarrier will be located at that point. I'll get back to that. I have wrote this in the notes, but I have to think about this one.
Okay.
So the next question is the following diagram may be explained on missing guard time for the UE at the cell edge and how they are received at the same time as the G node B. Okay. So I think you have interpreted this diagram in a wrong manner. This is what the base station has received. This is not what the UE has transmitted. Okay, this is what the base station has received. So the node, see, both these guys have started transmission at this boundary. You can see my cursor now. At this boundary, both the UEs have transmitted. Because this is a closer user, I mean the base station received it immediately. Okay, whereas this is the farther user, the one at the cell edge, that sequence came almost close to the edge. This is what the base station sees. See, this is a patch preamble received at the E node B. So effectively, this is a guard time that is being used by this particular UE at the cell edge. This is not the time at which the UE is transmitting. The UE, both the UEs have transmitted at this point only. Okay, so this is what the base station received. Okay, so now what will happen? The base station will do correlation. Once the base station does the correlation, it will find that the first sequence is very, very close to the boundary. So it has no guard time. No guard time is required. So no, what is that called? Timing advance is required. Whereas when the base station does the correlation here, we will observe that the sequence only started at this point. Then immediately it will be able to be identified that the timing advance that it requires is twice of this guard time or whatever, depending upon how it's computed. Is it clear?
Yes, sir.
It is not what the base is not. This is not the diagram on the UV where the UV transmits. The diagram of for which the base station received. Okay. Okay. So the next question, interesting question is for EMF. So base station radiation measurements have to be done. Okay. So the different technologies use different fixed channels in the system to do this measurements. For example, GSM they use BCCH, and in LTE they use the common cell-specific reference signal. The question is, what do we use? What can we use in 5G and now? Okay, so the problem, essentially the effective question is, what are the available time invariant signals in 5G for understanding EMF radiation? Okay, this is a very, very interesting question actually. See, the problem with 5G NR is there is no cell-specific reference signals. Everything is UE specific. The only thing that is transmitted always is the SS block. Okay, in some narrow bandwidth it's transmitted. Okay, so if you want to actually find, I would say the only time invariant signal is SS block. So you have to use the SS block for measurement, as there are no other cell-specific reference signals in 5G. But the problem is that SS block is a single port signal. If you look at the SS block specification, it says it's transmitted in port 4000. Okay, so what that means is you cannot use beamforming on SS block. They can use wide. Generally what they do is, they use wide angle beamforming for SS block, and not narrow beamforming for SS block, because SS block has to be broadcasted all over the cell. If that is fine, you can use SS block for your measurements. One more thing is PBCH might have power boosting. Okay, but once you decode PBCH and MIB, you will know whether power boosting is there or not. So you can compensate for that. That part you can do. Okay, but using a simple signal analyzer, it's a little bit more difficult, because you don't know whether power boosting is there or not by looking at just the spectrum of that part. Okay, so at this point, even the UVs also use SS block as a reference measurement. So I think the spectrum analysis and other things, if you want to measure the EMF and other things, SS block seems to be the most solid way of measuring. There's no other signal that you can be assured that will always be there.
So how we differentiate from RS, the reference signal in LTE it is available, why it is not available in 5G?
5G NR. Okay, so the idea, see, in LTE, Vijay, what happens is it was 20 megahertz bandwidth. Okay, 20 megahertz bandwidth, and the reference signal CSIRS, effect more important, it was transmitted across the entire spectrum, across all the 20 megahertz. Okay, so even if there are no users, the base station had to transmit the entire 20 megahertz, and it has to transmit the CSIRS. Okay, because of this, what happens specifically in night and all that, you cannot shut down the base station. The base station has to always operate, because CSIRS was, the reference signals were transmitted. Then 5G, they make this call that for power saving, you should be able to shut down a large portion of the base station, except where you transmit the synchronization block. Synchronization block is just 1.2 megahertz now. So you just transmit those 1.2 megahertz. And once that is done, once a UE gets locked, that particular part of the UE where it's serving can be on. That is the reason why there are no common cell reference signals in 5G, mainly for power saving for the base station.
Okay.
Okay, so but it's an interesting question. I will also think about it. What are the other signals that are there? How can we do? Sorry, my bad. Okay. The next question is, configuration 2 is used for LTE, downlink uplink ratio of 4:1. In Karnataka, all TSPs are using the above configuration. Why is there no gap available from downlink to uplink? Okay. I mean, I think you're not seeing the gap. There is a gap. So when they say 4:1, I mean, I'm just putting all the configurations for LTE. Okay. So when you say 4:1, this is a configuration 2 that they are using. Okay. So in the configuration 2, 3 slots are downlink, 1 slot is uplink, and 1 slot is a transition slot. Okay. In this transition slot, some symbols are downlink, some symbols are uplink, and there's a gap slot here, gap symbols. Okay. The specification says that the minimum number of gap symbols that are there in the transition at least should be 1. This is a specification. Okay. So until unless they are not following the specification, there will be at least 1 symbol which is a transition symbol. So when they say 4:1, it means that 4. So I mean, in the worst case, what they will do is they use 3 symbols downlink, 3 slots downlink, 12 symbols downlink, 1 symbol guard band, 1 symbol uplink, and 1 slot uplink. This is the, I mean, most aggressive configuration. Okay, there'll be some gap. In this plot, you are not able to see that gap because, I mean, you have to understand, I mean, your x-axis is in the milliseconds, tens of milliseconds range. Okay, whereas each symbol is few 64 microseconds or so. Some not 64, 1/30, 1/15 kilohertz. You figure out how much is that. Those many microseconds. Okay.
Then actually 2 days back also I tested, sir, CPM 10 milliseconds, and then I can go a little bit for 2 microseconds.
Yeah,
and
you
test
have
once
4
again.
microseconds. See.
Yes. Sir, you are not audible, sir.
Voice is not coming.
Hello, am I audible?
Yes, now only, sir. Before that, you are not audible, sir.
So my laptop suddenly died. I don't know for some reason. I think the power. I did not check the power. So I'm just joining from my iPad. Just give me 1 minute. I mean, so. Am I audible?
Yes,
Yes,
sir.
yes. Now it is audible.
Yeah. Sorry. I did not. I put the power, but it was not charging. I didn't realize that. Okay, so you can see that there will be some small transition time. You have to figure that out. So just look at this. So essentially, this is the configuration that's allowed. I mean, so I don't know if the later specification make this 0, but I don't think so. There's at least 1 guard, at least 1 symbol guard period is there.
So here in the above, for the uplink, the power transmission is less. That's why it is in the 40 microwatt per hour, sir, minute.
I do not understand.
Meter. No. Here, uplink. This in this diagram, 3 downlink plus S and 1 uplink is mentioned as here.
Yes.
Uplink range is 20 to 40 is there, whereas downlink range is 40 to 120. It is there. Sir.
So what is this you are showing me here?
So this is the electric field, sir.
Electric field.
Yeah, it is electric field. Left axis electric fields.
Okay, I think what is
normally we can radiate we can measure power, either power density or electric fields for measurement.
I don't think it's transmitting. This is a base station. A base station is not transmitting anything here. The uplink.
Maybe it is receiving, sir. It is a TDD, so
it's receiving. So this is the receiving signal. The blue one.
Yeah. Yes, sir.
Okay. Yeah, that's because it must be low power. That's all. Because the UV is transmitting.
No. Sorry. It is not a base station. It is not about base station, sir. It is the broadband measurement, sir. At this instant, what are the available signal strength it will show, sir. It is not for the BTS or not for the UE
So it's not
specific.
for the UV. Okay. Very,
Yes,
very,
sir.
okay. I will talk to you offline on this. I have to understand this curve a little bit more, and then maybe I can. There are 3 curves in this: min, average, and max. Okay. Why? Oh, these are not. Okay. Fine. I thought this was okay. Based blue was the UV. Okay. So I mean, the uplink you might be receiving. When in the uplink you might be receiving a little power from the base UVs. Now UVs might be transmitting. So the power that you receive in the what do you say in the UL is much more lower than the power that you are transmitting in the base station from the base station, which is makes sense.
Yeah, I am also thinking that way, sir.
Yeah. It makes sense. It makes perfect sense. Yeah. So, but the thing is, if you want to really understand how much is the time, you have to zoom a little bit into the millisecond range. Then you might see one slot. You compute, first of all, what you do is you compute the symbol duration for LTE. It's 1 by 15 kilohertz, na?
Yes, sir.
Approximately, other than the CP, that is 1 by 15 kilohertz. So you check if that part is a gap that is merging into the UL.
Yeah, I will test on Monday, sir. I will check.
Yeah, please do that. That will. Okay. So what I'm going to do is I'm going to stop at this point and we'll finish the next 2 questions because there's a little bit more detailed questions. I will do these next 2 questions in the next class. Okay, I will also give me some time to write it up and I will do it in the next class. It's already 10:40. Okay, so I'll see you on Tuesday again, all of you. Okay. Meanwhile, I would post these notes on MyMo. Please have a look at those notes and try to see if things are making sense to you, and we can try to answer the questions again. In the next. Okay.
Sir, please upload this class as the last 2 class and today's class.
I'll do that today. Today I'll write now. Okay. So thanks everyone. Thank you.